Today I will give you some brief review of previous lectures, and then we'll give you controllabilities either in linear systems and nonlinear systems. And they have used different approaches because of the dynamics. Last time I introduced you the equilibrium point. And the difference between linear system and nonlinear system is linear system has only one single equilibrium point. But for nonlinear systems, there might be multiple equilibrium points in the system. And how you take care of this equilibrium point is a critical topic, because not every equilibrium point are stable or unstable. But before we take care of the stability about the equilibrium point, we need to try to find where are the equilibrium points given the system dynamics. So for example, so here's the definition of the equilibrium point. A point xe is said to be an equilibrium point of the autonomous systems x dot equal to fx. If the system starts at the equilibrium point, and it always stays at equilibrium point. So it never leaves the equilibrium point, okay? For example, for the first example, here you can see a first order differential equations. It's a linear ODE, first order, okay? So given this system, you should be able to determine where are the equilibrium points, okay? So according to this definition, it says that the equilibrium point xe is the point that satisfies this equation. Okay, so what is f? F is whatever on the right hand side of the equation. Okay, and the left hand side is x dot. So in the first example, fx will be this part, right? Minus x. So what is the equilibrium point? According to the definition here, okay. So in the first example, fx is minus x, right? According to this, fxe will be 0, right? And fx is minus x, which implies x will be 0. So at x is 0, at x equal to 0 is an equilibrium point. Okay. So what's the physical meaning of equilibrium point? Maybe you can think about when fx equal to 0, right? It means x dot is 0. What is x dot? X dot is dynamics, right? Dynamics is defined as the time derivative of states. If this is 0, that means this x doesn't go anywhere, right? It stays there for all time. So stay there. So it stays here. That means whenever you substitute x into here, this one should be 0. Okay. So you can solve for x in the reverse way, right? So you let fx equal to 0, then you can solve for what is x. So example 2.目前讲的应该很简单吧，不需要翻译吧？好。So, example 2. Minus cosine x. So the equilibrium point xe will satisfy that minus cosine xe is 0. So given this equation, what is xe? And let me take a step back. Is a linear ODE? Is it linear? No. So you can expect to obtain multiple equilibrium points, right? So what is SE? Right? So you have multiple equilibrium points, okay? And here is a linear system, right? The first one is a linear system. So you have only one equilibrium point, okay? So example 3 is also nonlinear, right? Because of these square terms. So you will expect to obtain multiple equilibrium points. The third example, you got 2 equilibrium points, which are 0 and 1. Okay, so here, so this page told you how to obtain the equilibrium point. Okay, that's it. Any questions? If you are shy to answer my question whenever I say any question, you can shake your hand. Shake your head if you don't understand. Otherwise, I assume that you understand, okay? So next page, stability. Given those points, okay, given this equilibrium point, how did you evaluate the stabilities? Okay. So, so 3 cases. One is stable and unstable, and this one is in between. Okay. Okay. And here, the way we evaluate is take the partial derivative with respect to on f with respect to x, where the x is the equilibrium point. Okay. For example, so can you see this picture clearly? So this is phase portrait, okay, x1, x2. I did not write down the equations for this system, the dynamics equation, but you still can tell from this phase portrait to evaluate if this system is stable or unstable. So the difference is, for this picture, given, let's say here, the vector field is pointing to the right. 0 is here, right? So if you are on the left-hand side, the vector field is pointing to the right. That means that if you release or initial condition is at here, the trend or the velocity of the state is trying to go to the right. Okay. And what happens? So you will go all the way to the right until here, which is 0. And here there is no velocity. Okay. The arrow means velocity. Direction means, and the magnitude, it means the magnitude. In the phase portrait, the equilibrium point will be the point with 0 arrow, okay? With 0 is no vector there because it's stationary, it doesn't go anywhere, okay? I think this picture is not clear, so let me try here. Okay, is 0. And the first, the picture on the left-hand side is this. Okay, is that clear? So in this phase portrait, every point on the horizontal point to the point inwards. This one point outwards. Okay. Okay. So this one will be a stable case. This one will be unstable. Stable means you will converge to the origin. In this case. Okay. So is that clear? Anyone knows what's the meaning of this arrow? Okay. If I give you an differential equation, can you plot out this the phase portrait for this dynamic system? Can you? No. Okay. Let me keep this one. So the system, the phase portrait for this. Is so let's first try the 1D case. Zero is here. It's only one variable. It's just x, not x1, x2. Okay, so it's a 1D case. So the first you need to determine where is x. You can put anywhere. For example, if put x minus 1 here, you choose trying to determine the phase portrait. Every point in this axis. You can randomly first choose any location. Okay, let's say I choose minus 1. Okay. So given x is minus 1, what is x dot? 1, right? How about x is 1? And where's the equivalent point? X equal to 0. X dot will be 0. And this is equivalent point, right? X dot is 0. So equivalent point is here. And at x equal to minus 1, what's the velocity? The velocity will be 1. 1 means point to the right with magnitude 1. At x equal to 1, it's trying to move to the left. And how about at 0? 0 velocity. Okay? Understand? And here, in this page, we are talking about stability of the equivalent point. So we are talking about, we are care about the stability at this point. Okay? Because 0 velocity, right? So it's hard to imagine whether it's stable or unstable. But the reason that we take the partial derivative here is, remember what is f? F is velocity, right? F is velocity. And what about f partial with respect to x? Huh? Yeah, so what's the physical meaning? You can imagine kind of, yes, right? Right? So what does that say? That means given a little disturbance delta x, okay, given a little bit disturbance delta x, what will the change rate, what will be the change of f, right? In this case, f here is 0, right? Say f 0.1, delta x will be what? Minus delta x, right? Because of this, right? Okay, so minus delta x. So delta x, and what's the delta of f? This one minus this one, right? So it's minus delta x, which is minus 1. And if this partial is minus 1, it says it's stable. Because given a disturb, okay, f trying to decrease, which means it's trying to move back, right? 对吧? Okay. So it's like physically, it's like physically, given a disturb, you're trying to move back. Right? A ball in a ball, you're trying to move back. Understand? Otherwise, if for this case, it's like the reverse way. You put a ball here, trying to go off the 0, off the equilibrium point. Okay. So continue with the previous three examples. Okay. The first one is stable, right? Which is same as this one. Okay. The partial of f with respect to x is minus 1. And the second one, when you take the partial, is sine x. And remember, we have multiple equilibrium point here, right? So you substitute each equilibrium point as x in here, you will obtain different partials. So that says that this partial will be 1 whenever n is even. Otherwise, it's minus 1. Phase portrait of second order systems. So here is a second, so the A is a matrix, is a 2 by 2 matrix. So you can imagine that A will obtain 2 eigenvalues. Okay. For n by n matrix, ideally you can get n number of eigenvalues. So here are 4 cases. Okay, the first case is both eigenvalues are real, or both eigenvalues are complex, or non-zero multiple eigenvalues. Okay, or one is 0. One or both are zeros. So for the first order case, the dynamics of the system just looks like a ODE as the engineering math that you have taken on second year of your undergrad, right? 公司有学过的 ODE， 这没有什么不一样。And what if a second order? So the relation for x1, x2 is x2 is x1 dot. Okay. So imagine that okay, so if you have a car, the position of the car will be x1, okay, and x2, the x1 that will be x2, right? So x2 will be the x1 dot. Okay. So this is one example of second order systems. Okay. And usually, it's written in this way: x1, x2. Okay, so this is a matrix. Okay. You can convert this to this. So here you will put minus 1, minus 1, minus 1. Okay. 这样就一样了嘛，对吧？ And someone also say that, oh, these two basically this one is the time derivative of this one. So you can pull the derivative out, okay. Okay, and you can do it more simpler, like you define your x. Define. X defines x1, x2, which is a column vector of this two-dimensional column vector. With that being said, you can say x dot equal to some matrix. I call it AX. Then it's the same as this form. 能懂吗? So A is a matrix. A is a matrix. So what's the advantage of expressing in this form? 这样写有什么好处？这样写是跟 one dimension 的 is almost very similar to the expression for one dimension, right? For one dimension case, you here, okay? Second order. Okay, first order. So they are very similar, right? 很像，对不对？但是差在 this is the coefficient is -1. The coefficient is A matrix. Can you do further to compare the two? Okay, so at this time, the eigenvalue pops out. Okay, so wait a second. So here it's easier to tell that this system is stable, right? Because the coefficient is -1. Okay, you can either use that criteria, the stability of equilibrium point, or basically for me it's easier to tell that if it's -1, the coefficient is -1 is stable. If the coefficient is positive, is unstable. Okay. Is that straightforward to you? 这个不是 unstable， 这不 stable 是你们觉得这个直觉吗？不直觉，不直觉 ，OK。直觉吗？直觉，对，你就直接解它的solution就好了。对，比如你给它解出来，你解，sorry, what's your name? Niels. Yes. So does that make sense for you that this is a stable system and this is unstable? When the coefficient is 1, is that straightforward to you? Okay. And how did you tell? How did you tell that one is unstable, one is not stable?
Take the derivative, or it's a negative. The derivative, right?
Yeah, but why is stable? Give me what tool do you use to evaluate stable or unstable?
Usually pole placement.
Pole placement?
Yeah.
It's not necessary to be that complex. You can solve for the solution of x. 对，你们就解它的解嘛 ，ODE 这个应该很好解吧 ？OK， 但是你久以后你就不需要解了，你看就负的就正的你就知道这是 stable unstable。但是你要解就很快嘛。Like the solution of this one will be some coefficient that determined by the initial condition, right? And exponential of this coefficient minus t. So as t go to infinity, x will go to a 0, the equilibrium point, right? So on the other hand, if this is +1, you put plus here. As t go to infinity, this one goes to infinity, right? So it's unstable. But this, unfortunately, this is for linear system, right? Linear system, you can solve for the solution. For nonlinear system, if you are lucky, you can solve for the solution. Otherwise, you are not always lucky every day, right? Okay. So go back to here. So it's easier to tell the stability or just judge the coefficients, and you can tell that it's stable system. But how about A? A is a matrix. How will you tell? Basically, you use eigenvalue. Okay. Eigenvalue of A. Because A is a 2x2 matrix, you will obtain 2 eigenvalues. If both eigenvalues are negative, system is stable. Okay. If any one of the eigenvalues is positive, it is unstable. Okay. Because you still can solve the solution of x. in this two-dimensional second-order system, right? You can solve it and you can evaluate if that's right or correct or not. But basically, it's the analogy compared to second and first-order system. Okay. So the coefficient here is very important. And remember that the last time that if it's a positive x, we can add some control here to change the dynamics. So as we change the phase portrait, the vector field, and turn it over, right? Turn it from unstable to stable. Same as here, you can add some coefficient with your control. Okay, because x is a vector or two-dimensional vector, so b is also a two-dimensional column vector. Okay. Okay, so any questions? 有问题吗？ So let's go back to here, to the slides. So the first case, if both eigenvalues are real, just real, not positive, dimension is positive or negative, then the phase portrait there are many cases. Okay, 3 cases. The first case, stable mode, which is when both eigenvalues are negative. Eigenvalues. Let me say lambda 1, lambda 2. Real numbers. Both are real number and both are negative. And the phase portrait is a stable mode, and the phase portrait will be something like this. Okay. Just one of the example. Okay. Okay, it's a stable mode because the vector field is very consistent, right? It's trying to drive every point in the phase portrait to the origin. Okay. So it point outward from the equilibrium point, so it's unstable. And the third case, different signs. So one is positive, one is negative, or the other, or the other way. Okay. Okay. So this in this case is in between. Okay, if you put here, they are unstable. Okay. If you put here, and if you move in some direction, it's fine. But in this direction, it's not okay. Okay, because it's a mix. So one eigenvalue is positive, one is negative. In this area, it's not. It's unstable. It's unstable. But here, should be fine. Okay. Well, it's not fine. So, so this in this case is kind of this. Okay. In this case, it's kind of this. It's 2D, so it's a ball. Okay, so it's stable. Stay at the bottom. Stay at the top is unstable, and this one is a I don't know how to draw this picture. I will give you the picture online. Okay, it's kind of this set of point. It's so it's this and this. Okay, this and this. I'll give you pictures. Okay, so for complex numbers, for complex eigenvalues, for example, could be, okay, so for this case, beta, alpha, the solution is alpha plus plus minus beta I. So for the real, so for this real number is negative, is stable. Okay. So the difference between complex and the previous case, the real number is, you will see the spiral phenomena for complex case. See, but it is stable. So in the previous case, for the previous case, it's like this, right? For real eigenvalue with negative real eigenvalue is this. So both are stable, but this one is for complex eigenvalues. Okay. So if the real number part is positive, they will be unstable. So it goes outwards. Okay. And for alpha to be 0, only pure, which is pure imaginary part. There will be some demi-cycle oscillation. Okay, it's always in here. It doesn't go anywhere. Or in here. Depends on the initial condition. If your initial condition is here, okay, you will go this circle for all time. So this is the second case. For the third case, both eigenvalues, you will see two cases. If they are non-zero and multiple eigenvalue, if both are positive, if both you will see this converge to the equilibrium point. Goes away from the equilibrium point. Okay. And the final case, one or more eigenvalues are 0. First case, lambda 1 is 0. Okay. If 1 is 0, So if 1 is 0, it goes this way, and there's no, so the direction, this direction depends on the eigenvector, one of the eigenvalues. Okay, this direction. Okay, and there is no, because one of them is 0, so it's go one direction. It's kind of one way, okay? But the difference between this one and this one is stable, okay? Because it's point to, however you put here or here, we're trying to go back to this equilibrium point. But this one are different. This one is different. It goes outwards. Okay. And again, because one of eigenvalues is 0, one is negative. Okay. One is positive, so it goes outwards. Okay. And for this, okay, so because both eigenvalues are 0, their eigenvector will be, they will have the identical eigenvector, right? So this direction is determined by the eigenvectors, okay, of this eigenvalue. And one will go this way, one will go the other way, okay, and it's unstable, okay, it never stops, okay. But if you put here, if you put anywhere here, it will stand there. Okay, in this line, it will stand there because it's determined by the eigenvector, right? So if it's in here, the dynamics, the x star will be 0. So it will stand here. Okay. We mentioned this from previous lecture that the difference between autonomous and non-autonomous systems. Okay. For autonomous systems, a system is not, it doesn't explicitly depend on time. So compared to the non-autonomous systems, the dynamics explicitly depend on time. Okay. And here, all the coefficients don't depend on time. Okay. Coefficients -1, right? So it doesn't depend on time, but here you have time as dynamics. So that's the difference. But what's the difference? What's the difference when you compare their phase portraits? So this one on the left-hand side is the autonomous system, and this one is non-autonomous systems. So at time equal to 0, the phase portraits is this and this. They are the same. Okay. Basically, they are the same. So the dynamics, the only difference in the dynamics are this plus t part. So at t equal to 0, the dynamics is the same. So given the dynamics, you can find their corresponding phase portraits, 对吧? Okay, so how about at t equal to 1? At t equal to 1, it remains the same because the dynamics never changes, right? It never changes. But here, t equal to 1. So compared to t equal to 0, this equilibrium point moves up to here, right? Right? And at the next time, t equal to 2, you keep moving to the upper left. Okay. So that's the difference between autonomous and non-autonomous systems. So you can imagine that this one is more trickier when you design the controller for this one. Controllabilities. Lemma is given a system, a linear system, a linear time invariant system, because A and B assume to be a constant coefficient, okay? And this system is said to be controllable if this C matrix, which is B vector And here's another vector, which is a product of A and B, A squared B. So if this matrix is a full rank, we say the system is controllable. Okay. Why? So in the linear control system, usually we just introduce this, and it's the tool that you can use to evaluate. But why? So imagine that. So this is A matrix, B vector. Okay, B can be a matrix too, but here is a vector because we assume U is a one dimension. B can also be a vector. There is a column vector, right? But here it can be a matrix too, like 1, 0, 0, 1. And U will no longer be a scalar. It will be a vector 2. Okay, if you have multiple input. Okay, here is only single input. Here is multiple input. Okay. So this system is like a robotic system, robot arm, and you have only one joint. Joint, the voltage to the joint, which might be a motor, is the control input, right? If you have two joint robots, you have two inputs, and in this case, you have to use this model, okay? Okay. And this x could be the end effect, the position and velocity of the end effect. Okay, end effector， 知道什么是 end effector 吗？就是那个最端点那个位置。好 ，so in this case we assume it's a single input system for simplicity. So why the controllability can be, why this lemma can be used to tell the controllability. So the reason is, assume that you have U given here, which is coming to the system. So this U, because of the B matrix 0, 1, this U at the T0, it only affect the X double dot, right? So at U only affect the X double dot at T equal to 0, right? Let me span out this system. Span this into a two equation system. On the left hand side of the equation, it equal to this, right? 对吧? And how about next? It equal to X dot plus 0. This one is X 0 plus U. Right? So 0, we just keep it clean. So basically it's this kind of system. Okay. So of course, for this kind of system, your control input can affect the acceleration, right? It can control the acceleration, right? Like when you drive the car, the pedal control the amount of gas put into your engine. So that means the pedal control the acceleration of your car, 对吧？你的油门是控制你的加速度，对吧？ But the controllability want to see if your control can not only affect this state, can affect both states. We want to see if your control input can affect both states in time. Okay. 听得懂吗？它 controllability 就是说，看你的 given 一个 control， 你能不能控制到两个 state。在这边呢，因为 because it's an equation, we can see that it can control the acceleration. But what we wonder if we can control all the states, which are position and velocities. Okay, but for sure it can control acceleration. But as time goes, it's hard to say, right? So let's see the next time at t equal to 1. What happens? Using that equation, okay? Okay, here's our objective. Okay. So at t equal to 0 for any time, your input can control the acceleration. But how about the next time t equal to t1? We know that after this duration, right? After delta t equal to t1 equal to t0 plus delta t, and the acceleration here, if you do the integration here, you will obtain that x1 dot x dot at t1 will be x t0 times delta t, right？ 你的速度从原本的 t0 到 t1，这个的差是由加速度造成的嘛，对吧？ The acceleration can change the difference of velocity in time, right? As long as it's not 0, right? Okay, 对吧 ？Okay. How about S? So here we can conclude that. And where does this come from? This comes from here, right? If your U is 0, this is 0, and these two will be the same. But the difference, but now we know it's non-zero, so they are different between T1, the X star at T1 and T2, right? So that means that you can control X dot, right? So this one is okay. How about this one? T1, T2, T2. The position state at T2 will be approximately right. The displacement at T1 and T2 will be different if you have a velocity, right? What's the relation between this velocity and control? We want to see that objective, right? Control versus the position states, if they have some relation, if they can control. So if these two are different, that means that the state can be changed, if only if you have non-zero velocity, right? But how did this non-zero velocity come from? It comes from here, it comes from here. So this will be this can be changed from here to here if only if the acceleration is not 0, right? And this comes from the control. So that means that if U is non-zero, it can control x, right? U can control velocity, and velocity can control your displacement, right? So you can control x. So so this system is controllable. Okay. So what's the relation between these three time step and this matrix? So that's because for this column is B, right? C is matrix, which is B and AB. So at t equal to 0, so that B is this, B is this, right? 0, 1. So that means the control come into a system to affect the second element, which is x double dot, right? But as time goes, x double dot will be integrated to affect x. So you can affect the second state. So it's 0, 1. Okay? You can change the second state. But as t goes to the next step, so you can control x dot. You can control x dot. And x dot is the second element, right? So in the next time, this state, which is controlled by the control, can affect the first element here. So it's become 1, 0. And this comes from A times B. Okay? Because if your A, because when you use this state, this have been controlled, have been affected by U, right? So when you multiply this to this, the inference will come in from the second state to the first state because it's put 1 here, right? The second element times this will transit to the first element. 这个 U 啊，它是直接控制这个第二个 element。U 是直接控制第二个 element。那 control 加速度就是可能 control 速度嘛，因为随着时间变，加速度也就变速度嘛，对不对？所以这个呢一定会影响第二个 element， 也就是 x dot， 一定会影响第二个 element。那第二个 element 会不会影响第一个 element， 就由 A matrix 决定的，对不对 ？A matrix，I know that 这个已经被那个 control 可以影响。那如果这个呢，透过这个 transition matrix， 透过这个 matrix 可以被影响第一个 element， 那也就是说 U 可以 control 第一个 element 的，不止 control 第二个，也 control 第一个的，对不对？所以你看这个，它乘以它以后会发生什么事？这个 element 是会被影响，然后乘进去以后是刚好乘到一不为顶，而且乘完之后它会放到第一个 element， 对吧？所以 U 不只影响第二个，也会影响第一个。那第二个到第一个功劳就是靠它 ，OK？ But here is a more systematic way to verify the controllability. But here is the background. Okay. Understand? Run 重段，你听得懂吗？ Okay. Okay. So Niels,
Yes.
can you understand? So you can change acceleration, right? But as t goes, you cannot stop time, right? Time will goes forever. So as time goes, x double dot will change the x dot, right? Which means this one will be controlled by U. How about the first element? We know this element can be controlled, right? But if there's an inference from here to here, that means that you can control both this and this, right? Where did the inference come from? It comes from this A matrix. Because we know this one times this one, the second element times this one, which is non-zero, right? After it times this one, the product will be equal to the first element, right? And as t goes, the x dot will be x. That means you can control both this element and this element. Okay. So you not only you have to use B column, but also as AB, right? But how about you have a three-dimensional system? Then you need to use B, AB, and A squared B. Right? You need one more time step to see if the second element can change the first element. Okay. 懂吗? So what? So how about? So in which case it's not controllable? If I so how the question is how can I modify A or B such that it's not controllable? Very simple. Let me show you. So originally the system is this. If I swap these two, the system will be not controllable. Okay. 如果两个调换它就不 controllable， 你可以试一下，为什么呢？如果我 swap 之后，它会变怎样 ？C matrix will be 1 0, right? This is B. How about AB? AB will be 0 0. It's not full rank, so it's not controllable. The reason is when you swap this 0 1, it becomes 1 0. When it becomes 1 0, you affect coming to the system to affect the first equation, right? So you affect x dot, right? You affect x dot. So x dot as t goes, it change delta x. So this x will be changed. But at the next time, if the change of this x, when you use this times this, there is no, the second element is still not changed, right? Because it's 0 1. But 1 0, but here is 0 1. So after you times this is 0 0, which is 0 0. So there is no inference from the first state to the second state. 听懂吗？不懂。当你原本是0 1，你现在换1 0的时候 ，control 是影响第一个 equation， 对不对 ？control 现在是从第一个 equation 进来，它会改变 x dot， 那随时间演变 x dot 是会改变它的 x， 所以只有第一个 state 会被影响。那影响的第一个 state， 它会影响第二个吗？你就看 A matrix 嘛。看这个嘛 ，OK， 它被影响了，sorry， 它被 control 影响了，所以它的 s 会变嘛 ，s 乘以这个以后是怎样 ？s 乘进来以后，这个是0 0嘛，对，0 0嘛，所以它的改变不会造成第二个 element 改变嘛，懂吗？除非你把这个换过来，把这个变成是变成这个是1。那这个的影响呢？它乘以这个 matrix 之后，就会跑到第二个的，能懂吗？了解。But how about the nonlinear systems? So the previous slides for linear system, controllability for linear systems. How about for nonlinear systems? It's more complicated. Why? Because in the previous slides, this guy is a constant, right? It's not a function of x. But for nonlinear systems, this g can be a function of x. That means once you change the state, this matrix will also change. So it's become very complicated every time it changes. So, so the criteria in this linear case can no longer be applied. We need a new criteria. For example, in this case, f could be x squared. G of x u could be xu. Okay, so this x changes every time. Okay. So here is some example that it's like a turtle bar. Okay. So the dynamics is you have only one control. So in the first case, these two examples. The first case is the u dot is not controllable. Second case is u dot is controllable. There's a second control. Here's only one control, u1. Here's u1, u2. Okay. So what is x and y? X, y is the coordinate system in the global is a global coordinate system, Earth fixed, and this is body fixed. So this u1 is the linear velocity of this vehicle. Okay, so you can control the linear velocity moving forward. Okay, you can control the speed. But this angular velocity of this vehicle is not controllable for the first example. But the second example is you can control, you can steering the vehicle, like, understand? 就像第一个 case 就是说，你只能踩油门，你不能控制方向盘。第二个是你能踩油门，也能控制方向盘，能懂吗？ So we want to see, given these examples, we want to see which one is controllable. So of course, it's a nonlinear system, right? Which satisfies these criteria. And we want to see if this system is controllable or not. Okay. So we stop here. If you have time, I will post the videos once it's available online to the YouTube, so you can review today's lectures. Because that, if you don't quite understand or quite sure the material that being covered today, maybe you have difficulty to understand the next lecture. Okay, because it's for nonlinear systems. Okay.